All right, so let's look at flexure and compression. So we went through pure compression, but that's typically not what we're going to see. It will either have some kind of wind load or some other kind of lateral load that's causing bending, in addition to axial load that comes from the, go ahead and here, from the joists or whatever's above, right, funneling into here. And this lateral force can be in this direction, like it's shown, or it can be in and out of the paper. So that would be out of plane bending. The example I'm going to do is out of plane bending, which is similar to the bending, the flexure we did for pure flexure. All right. Um, the time you're going to use this wall in this direction for bending is more along the lines of when we're using these as our shear walls, right? We're not going to go into that level of depth. There's a lot going on with those, and particularly if you're in a seismic region. So we're just going to look at how the axial load and bending that we've already done in that same direction, so loaded on the face of this wall, would work. But the way I'm going to show this to you, the equations work for both either direction. Okay, it works the same way. You just need to know that this is the height or the depth of your cross section in one direction, and this would be the depth along the length of the wall in the other. Okay. All right. So most walls are going to have both axial compression and flexure because even if I don't have the lateral forces, I'm going to often have the loads framing in at some eccentricity, so not dead center. And it's the interaction forces which we see. Um, this is similar to reinforced concrete. The difference here is that instead of all those nice interaction diagram tables, the ones that kind of look like, this or more rounded, in the case of masonry, for all the different kinds of wall cases we'd have and types of block sections, we don't have a ton of those tables. So I need to teach you how to do the basics on this. All right. So I think what we'll do is just jump in. This is in section 5.5 of the handbook combined, so you can see where we left off before. And now we're into combined flexure and compression. And you'll see some of the same pictures that I've got on the slides. All right, so you can follow along in the handbook. This is basically from the handbook. It's just blown up so you can see it a little easier than me scrolling through the handbook. All right, so first of all, we need to make this interaction diagram. So there's going to be some type of thing. If I was doing concrete, I'd have my P and my moment, right, like this, and I'd end up with the case of pure axial. Okay, so no moment at all. And then I'd have some other cases along here. We have balanced, we have another case along here, and then we typically have where it kicks back in this direction, and I come up with an interaction diagram. So I'm going to do kind of the same thing and just show you the points that you'd have for the masonry. It's a similar thing. So the first case is pure axial. So this is, I've got an axial load P and I've got no moment, so no bending. So that's the purest case. We're not usually going to see that, but that's the very tip of the interaction diagram. Okay. If I start looking at putting a little bit of moment on this, I can go ahead and put moment on for a while and still just basically have, so here's pure axial, stage one. Stage two is I put a little bending on, but I'm still in compression at top and bottom or outside and inside of this wall face. All right, so this is a basic interaction that we also have to check, that the bending plus, axial plus bending stresses less than or equal to 0.45 of the strength of the masonry. Okay, that's a TMS requirement. We'll do this when we go through the example. Now we're in stage three. Okay, this is going to be 0.3 on the interaction diagram. Now we're going to be at a place where if I have my stress diagram, okay, so we're looking down on the masonry and the steel at this point. Okay, and for these walls, depending on, I'll show you at the end, but I want the steel on the quote tension face, and I'll tell you what that means when we look at the different sides of the wall. Right, but here now I'm going to have zero tension and I have some amount of compression. Stage four, now I'm going to have a little more moment. so that I am now at the point of 0 force at the level of the reinforcement. So I was 0 here. Now I've moved up to 0 at the level of reinforcement. And then finally, I'm going to move into the case where I've got my tensile component, my compressive component. Remember, we're not using a block here. And we're assuming that the compression in the masonry, and we've got the steel is carrying all of the tension. So, like I said, there's published interaction diagrams for concrete, and then we can figure out the reinforcing from those interaction diagrams, kind of tell us, given equations. We can make those same things for concrete masonry. You can make a spreadsheet for it that generates them, but they're just not as common to have everything tabulated. So if you're working with a certain type of block or so, you could make a spreadsheet for this if you're doing this in practice. And you would just pick those points that I just showed you. So what does this look like? This is point 1, 2, 3, 4, and 5 that we just did. And the top line here is for a height of 0 feet, in other words, a completely braced, and it would just be the axial compression. But let's look at, say, for 12 feet. So this is the actual interaction diagram in masonry for the 12-foot case. Okay, and then it goes back. And then this solid line coming all the way back would be if it was at a height of 24 feet. So they're just giving you an example for one type of wall. Okay. And what they're showing you here is also that basically if you're in this first region here, so let's say I'm using the red interaction diagram, it's basically all about the axial stress, and we're limited by how much axial stress the masonry can take. If I'm in this middle region, it depends on the slenderness, okay, of the wall. Okay, so some bending due to slenderness or axial, where we start to bend out of the plane, and allowable axial or bending stress in the masonry. Okay, so the capacity slenderness is giving us an account here. In the C region, which is this dark one, it's limited by bending stress in the masonry. Okay, it's if we've got enough moment that bending is really the issue here. And then finally, in this white region down at the bottom, D, this is limited by how much tensile stress I can take in the steel. All right, so that's how you do these guys. All right, so this goes through what I just said with A, B, C, and D. Okay, so you have this in your notes. So how do you do this? The last method, there's 4+ design methods, okay? The fourth method involves making the interaction diagram, like what I just showed you, but going through all the calculations. There are 3 other methods. I'm not going to go through each of these. They're each in this handbook section. So they'll go through and they show you what I just showed you here. Right? So you have all these notes basically in your handbook. Shows you this interaction diagram we just looked at. This one is if I actually have confinement of the reinforcement, but we talked about that that's not very common in walls. Okay, so now methods of design: 1, modified 1, 2, 3, modified 3, and 4. All right, so you can go through these different methods, but I'm going to skip to the part that we're interested in, and that is the method that we will typically use, particularly here in Minnesota. All right, so there's method 3 and modified method 3. Okay, so this is modified method 3 is in section 5.5.2.5 of the handbook. So if you go into that, that will give you how each one of these is derived. 5.5.2.5, almost there. Yeah, they have a bunch of examples. So modified method 3, this is what we have here, and they go through how this is done. So I'm just going to show you, sorry. This is the most common method. This is the only method for your homework or for the exam that you're responsible for, okay? More direct solution of reinforcement. Okay, so typically these are controlled by tensile stress, and we'll check that. but this is a more direct solution than some of the others that are in here. It's appropriate for sections that only with tension only reinforcement, in other words, no compression reinforcement, which we haven't done anyway, and it doesn't add that much. And it's most commonly used one, as I mentioned. And let me talk a little bit about where the reinforcement goes in these things. So let's say I've got, there's my block, here's another block, and here's another block. If I've got the lateral load coming from this direction, the tensile steel is basically concentrated here, right? So I can have some steel in these different voids towards the edge. If the wind or seismic comes from this direction, I need it over here. So what you'll see in those walls, if I draw the wall section, you'll see reinforcement kind of clustered towards the edges. That's what's true in concrete shear walls as well. Or you can go ahead and have it all along. What will happen if I want loads in this direction? It's the same type of thing, but because I've got the same case where I'd like to have them closer to the tensile face if it's coming here and closer to the tensile face here, but we know there's only the hollow cavity. So most of the time I'm going to put it right in the middle and just do that all along the length. Obviously, it wouldn't necessarily be in every cavity. It'll be at some factor of 8, like 24, 48, something like that. Okay, so we're looking at this case where this will be, again, in the center. The bending is in and out of plane, or is out of plane. But the same type of thing happens here when you go in the in-plane bending. All right, so let's go ahead and take a look at this. Modified method 3. Okay, so the way this works is you figure out if it's tension or compression controlled. You apply a P force to the section and solve for imbalance. So just leave it as P. If it's compression controlled, you'd use the plane method 3. If it's tension controlled, you use modified method 3. We are only going to do tension controlled sections. And you go to step 3. Okay. Here's the derivation of imbalanced. Now this is literally algebra, so I'm not going to go through it, and it's also in the handbook. All right, hang on just a second here. So it's also in the handbook. Sorry, I have a little dog issue I'm taking care of here. Okay. So when I get through that derivation, which I said is algebra and substitution, this is what I get. When I have the case where that D1, which is the distance to the steel, is actually L over 2, this term will drop out. So for most of what we're doing, the actual equation is here. All right. If I can look up K-balanced, and it depends on the masonry. If I'm using normal CMU block, grade 60 steel, which is pretty much what we're going to use, you can use this value for K-balanced, which comes from the K-balance equation, right? And that also gives us a J-balance here, and the JK at the balance section is 0.279. All right, so out of plane bending, which is what we're doing, rebar L over 2, and that's what I just did up there, right? It's just the simplified equation. Just like in concrete, if the moment is bigger than imbalance, it's compression controlled. If it's less than imbalance, it's tension controlled. And tension controlled is basically the bending type, the more heavily bending type sections. All right, so I'm going to stop there, and I will do the example for this section. You will have a very similar example, or a similar one for your homework. And likewise, on the final masonry test, you will have bending, same direction, out of plane, combined with axial. That will be one of the problems. All right.